of like in between both a liquid and a solid, kind of at the same time. So this right here is something called Pélé's hair. Pélé's hair are these very thin filaments of lava. Pélé's hair do get formed in nature, but this is something that will happen when lava goes off of an edge and picked up by wind. And that's how it can get blown into very thin strands like that. These are named after the Hawaiian goddess of volcanoes. Her name's Pele, except in Iceland there is no such thing as Pele. So in Icelandic, these hairs got called witches' hairs, or Nornahal. Pélé's hair get cooled down very quickly. They go from orange to black in just a few seconds. Because of how thin they are, that does make them pretty rare to find in nature. Just because around erupting volcanoes, something that small, it does get destroyed immediately. So here I have a second block of ice. This one is going to go on top of the lava. There. And then I'll just add some pressure. And a flash. As you can see, we had something very different happen this time. We did not get lots of bubbles. We got one kind of little one there, but we can also see the lava sort of inflated. So if you look at the surface of the lava isn't moving anymore. The top layer begins to solidify very, very fast. So this time, when the block of ice goes on top of it, it does turn to steam. We can see steam, but some of that steam is also getting trapped in the lava. So as the trapped steam tries to get up and out, it will instead inflate the lava up, kind of just like a balloon. And sort of an inflated lava instead. Now lava is a pretty good insulator for heat, and it will be creating sort of an insulation for itself. So I'm just going to poke at the top there. You can press down on it. And we can definitely see that for sure is not liquid at the top anymore. But what I'm going to do is I'm just going to get underneath this part here. And then I'm just going to gently lift it up. So you can see that outside, especially the top, is going to hold shape, but it's bending. And underneath, you can see it's not solid on the underside. Because that top layer of insulation in the sides, it's protecting the under part, protecting the inside lava. It's allowing it to stay hot for longer. But once it comes out of that insulation, it is going to start to slow down. It is going to start to solidify. So I can take some of this out here. So you can see this texture change. We're going to have a little bit of a weird texture lava now. It's sticky and it's globby. Because liquid lava can't go straight from a liquid right into a solid. It has this middle ground where it's sort of both and neither right at the same time. You can see in the parts where it turns thin, it's going to go black. And I can bend it, and I can manipulate it, but that outside shape is going to hold. Now, I'm going to try and get into here now. Whoa. So we're going to go into here, crack it just like an egg. Okay. It is glass. We're going to get to that, I promise. But all right, so even inside of here, I'm just going to lift this up. So even that tiny thin shell of my lava egg, it's going to be enough to keep that inside hot. But we definitely have a funny texture now because you can see it's not pulling apart at all anymore. It's holding together and it stretches and stretches and stretches. But eventually it is going to reach a point where it doesn't really let me stretch because even if I have all of my weight down on it, it's moving just ever so slightly, but I think here is where it's not going to stretch anymore. It is we can see at the base it's starting to turn a little bit black. You can see up here where I have the stick, it's definitely got a lot of black up there because we're at a full solid. Now, we're going to listen to this sound that it's making. gentle sort of noise. Crackling. I always think it kind of sounds like Rice Krispies when you add milk. What this sound is the sound of the lava becoming solid. Because solidifying lava, as it cools down, what it's doing is shrinking. As the lava shrinks, it has to contract into itself. And so this is what we're hearing. We're hearing a cooling and contraction of the lava as it's becoming more and more solid. Right now, it's a very gentle noise. The sound will get louder as the show continues. It's just a touch here in the front, just like that. All right. Now this process of how the lava has created that solid outer layer that holds, but then the middle section is going to stay hot and liquid for longer. That's the process in nature. This is what's going to cause lava tunnels to form. So in nature, when there is something called an effusive type of eruption, and effusive eruptions, that's the opposite of an explosive eruption, because effusive eruptions are the gentle kind, basically as gentle as a volcano can be. There can be very nice rivers of lava that form, where they pour out of the volcano, and then they flow and they burn their way through landscape. But over time, even something like a lava river will lose heat, it's going to cool down, it's going to become solid. But it only becomes solid on the outside, because it creates that layer of insulation. The middle section can't cool down. It's going to stay hot, liquid, and flowing for a much longer period of time, as well as it's going to flow a longer distance until that volcano stops erupting. Eventually, volcanoes do stop. When this happens, all that liquid lava flowing in that insulation can flow and drain itself out. What gets left behind is that solid layer itself. And so that's what a lava tunnel is. It's just a hollowed out, hard part that had formed itself around the lava river. You kind of think of it as like an emptied out water. So I'm going to grab my temperature reader right here. And I can give you an update of where the lava is at.
I really want you to break that.
Yeah, I will, I promise. All right, so when the lava came into the room, it was 1,100 degrees Celsius, that's 2,000 Fahrenheit. Where the ice was, that's going to be the coldest part of it. So where I put that ice has dropped down to a very, very chilly, it's actually pretty low, 432 degrees Celsius, 810 degrees Fahrenheit. Back here, we're going to be hotter. Back here, 656 degrees Celsius, 1,212 degrees Fahrenheit, and then I'll take from here as well. On the other side, where we didn't have the ice, it's just a tiny bit hotter, 713 degrees Celsius, 1,315 degrees Fahrenheit. So here I have, it is just a little bit of paper, and so this is going to go on the lava. Let's see, where should I put it? Okay, I'll put one here. I'll put one here. Of course, it is going to catch on fire, and there you have it, homemade lava lamp. Ah, thanks. All right, your wish is going to come true.
Yes! That was nice.
Very satisfying, yes. But all right, yes, this sound is going to be very, very familiar. I have heard you guys say it. Sounds a lot like what? Glass, yes. Because that's what it is, except it is not regular glass, it's volcanic glass, which is cooler. Because volcanic glass is what gets formed when lava gets cooled down really fast. So fast that there's no time for crystals to grow in it. That's the definition of volcanic glass. It's lava with no crystals in it. What that means is as the lava is becoming the solid lava, the elements that make up what it is, they are grabbing to all of the other elements around them to start creating bonds and build solid structure from it. Except when it happens too fast, elements, they don't have time to build things super complicated, like crystals. All they got time to do, grab to whatever's right next to them and just become a solid. So they tend to grab to whatever's most readily available, whatever is most abundant, whatever the lava's mostly made out of, which is silica. Silica is 47% of this lava, almost half of it, just silica. When everything bonds to silica, everything looks like silica. Silica is also the main ingredient and regular glass. That's how we get the volcanic glass instead. So fast-cooled lava with no crystals, but everything bonded to silica. It's also black in color though. It's not clear like regular glass because there's other stuff in it too. Specifically, it's the iron in it. That's what's going to cause it to be black instead of it actually being a true clear. Now, one question that I get all the time is this obsidian? The answer is no, it is not obsidian, but it sure looks exactly the same as it. So a lot of the times in like pop culture, especially because of like Minecraft or Game of Thrones, obsidian is often used interchangeably with the word volcanic glass. But in geology, there is going to be a little bit of a difference because volcanic glass is a generalized term. There are many kinds of volcanic glass in geology, and obsidian is just one of those kinds. But for a volcanic glass to be given the name to be called actual obsidian, it has to have a different chemistry. The lava has to contain 70% silica. Our lava is only 47%, so it doesn't count. It's not obsidian because of that chemical technicality. This one at 47% silica, instead it gets called tachiolite. It's not as catchy of a name though, but it does look exactly the same. It is formed in the exact same way. But geologically, because of the chemistry difference, it is going to cause a slightly different name. All right, so I'm just going to hold up this piece here so that everybody can see just sort of what the inside of it looks like. Just so you can see how it's got the black outside. It's the part that started cooling became solid first. It's the insulation. So that the middle section is just going to stay hotter, it's going to stay protected for a longer period of time. But once I break that insulation, once I disturb that seal around it, lava will release the heat fast. As it cools down, the glow will fade away, and eventually we're left with the entirely black lava. Now the reason why it does that, why it starts off glowing, but as it cools down, it fades away. It's because when the lava is really hot, there's a lot of energy in it. A lot of energy that gets released in the form of light, because light is a type of energy. It happens when lava is above 600 degrees Celsius, 1100-ish degrees Fahrenheit, because there's a lot of energy, so nice big glow. But when it cools down too much, not as much energy. Therefore, no more glow. It does fade away, and we end up with the solid black lava. Now, I will turn off the lights a lot more now here in the front so that everybody can see that surface. I know. See, it looks safe to touch. We can give it a temperature read, so we can just go down here in the puddle of it. So we'll see at the surface. We're at 544 degrees Celsius, 1012 degrees Fahrenheit on it. Right. But yeah, do I have other questions? Feel free to ask. Yeah?
How is the pumice or the lava rock that's full of little bubbles? How is that formed?
Yeah. So, yeah, pumice and lava rocks full of holes. How is that formed? So, lava rocks in nature, a lot of the times, we'll do a difference. We'll do the standard lava rock and the pumice, because, yeah. So we'll start with standard lava rock, because normal lava rock also does have a fair amount of holes. It almost looks like sponges. That's going to have to do with gases that are coming out of the lava. When lava is being erupted from inside the earth, it's also bringing up with it toxic gases, sulfur dioxide, things like that. And so when the gases are coming out, it's a process called degassing. Gases in a liquid look like a bubble. And so all the pores you see in lava rocks, it's because that's just remnant evidence of where gas bubbles used to be at the time that the lava became solid. So that's how you get sort of the standard one. Pumice is just sort of an extreme version of that It could be for a couple different reasons. Pumice is a lava that was either just super, super gassy, like it had an unusual amount of gas in it, and so it just there were so many gas bubbles, it just created this light, fluffy rock. Or you can get pumice from lava like erupting directly into the ocean, because the rapid expansion of steam is just going to go whoop and just fill it with a bunch of gas bubbles, steam bubbles, and then it solidifies. So yeah, a standard lava rock is just the gases. Pumice is just a more extreme version of it. And that's actually why our lava doesn't have those holes in it. We don't have pores in ours, because our lava does not contain any gases whatsoever in it. It's all gone. Yeah, where did we get the lava from? So we picked it up about 2.5-ish hours away from here, near a town called Vik. So Vik is a town that sits right next to the volcano Katla, and the material specifically is from the 1918 eruption of Katla. Just east of that town, there's a whole big giant field of Katla lava. So we pick it up out there. Yes, exactly. So we pick it up and we reheat it. We have a big giant, it's a metal furnace back there. It's an industrial metal furnace that just has had some modification done to it to melt lava. So we pick it up when it looks like this, the black sand in here, because this is lava, just tiny pieces of it. So how this lava got formed though, because the lava we pick up, it looks very different than what we pour out in front of you. That's because it's the same lava, but different environments of formation. The glass turned to the glass because it cooled down quickly. That's the only reason why it looks like the glass. This in here, earlier I called it basalt tephra, which is its official geological name. So the basalt is the type of lava that it is. Tephra means exploded pieces of rocks. So the basalt tephra is what got formed when Katla erupted with its glacier on top of it. The glacier on top of Katla is huge. It's twice the size of Reykjavik. It's up to 700 meters thick. That's about 2,300 feet of ice. That's a lot of ice that's going to be up there with an erupting volcano. So when a volcano like that erupts with that much ice, the lava is going to come up. Lava interacts with ice. It's going to melt it. You get water, ice, lava, and that equals ginormous explosions that are constantly blasting that lava apart into a million, billion, trillion tiny little pieces. And that's what the tephra is. It's small exploded pieces of lava from explosions. But over time, eventually all of this stuff up there, it is actually going to come down because eventually enough ice is going to melt. We're going to get a massive flood because of it. In Icelandic, it's called a jökulhlaup. It's a glacial outburst flood. It comes crashing down, brings down water, icebergs, and all of our exploded lava here. Water goes out to the ocean, and then what ends up getting deposited on the land is a black sand desert, as well as a few black sand beaches. That's where a lot of this stuff is coming from in Iceland. Most of it is not erosional sand. Most of it is from exploded lava in the volcanoes and brought down, deposited by a flood. This eruption of Katla was particularly large. This brought down so much of the exploded lava, it added 5 kilometers to the coastline. That's about 3 miles. So it's a lot of material. That's one eruption. From there, we just go to the part that has 1918 stuff on it, scoop it, throw it into the furnace, and then we have new lava. That's how we do it. That's where we get it. Sorry? How did they all erupt from Iceland? How often? Oh, we get, how often does a volcano erupt in Iceland? Usually it's one eruption every 3 to 5 years. But we've had a very active time. In the last 3 years alone, we have had 8 eruptions. But it's supposed to be every 3 to 5 years we get one. We've just been in a very active time. All right, so he asked, do we recycle it? Yes, we do recycle the lava, so all of this can get cleaned back up. That's exactly what Mario's gonna do when everybody leaves the room. He's gonna scoop this all out of here, and then he takes it to the back, and he can put it back into the furnace. We are not chemically changing anything about our lava. We're changing the state of matter, whether we have liquid or solid. So we can take it, throw it in there, melt it down. We don't see any changes, so it's really nice. Yeah.
Are all lavas across Iceland chemically the same?
Are all lavas across Iceland chemically the same? For the most part, yes. So basically 90% of Iceland is made up of this kind of lava. There is that other 10% that is a little bit different, but we can just go ahead and say most of Iceland is going to be this type of lava. It's the basalt type. There's three kinds of lava, three basic kinds of lava. We have the basalt, and then we have one called andesite, and we have one called rhyolite. So the other 10% is a mix of andesite and rhyolite. Mm-hmm. Yeah?
What happens if you put lava on top of that?
Yeah, what would happen if we put more lava on top of that? So what would happen is that it would just sort of go on top of it. It wouldn't fully remelt this, but it would melt enough to stick to it. And it would just make another layer. It would kind of look like a 2-layered cake, is what it would look like. We would just get 2 distinct layers of lava, but you would never be able to pull them apart. They would stick to each other. Yeah?
Earlier you said Mario had no staying on his
Mm-hmm.
radiation.
Mm-hmm.
Where is that radiation coming from?
Oh yeah, so the gold film on his helmet, where's the radiation? It's just the radiant heat. So it's just the blast of heat, as well as the light. Because when he looks through it, it's basically, it blocks off so much light, he's like wearing a big sunglasses over his face, but it also doesn't allow any heat in. Yeah, so it's not any like dangerous radiation, it's just the heat radiation. Yeah, because when he opens the furnace has to run hotter than 1100. It runs at 1300 Celsius. And he does, unfortunately, have to hand shovel lava into that furnace. So he has a big thing to protect his face. Yeah. Yeah?
How does the eruption affect the ozone layers?
How does the eruption affect the ozone layer? Oh, it doesn't really affect the ozone layer. It does affect things in the lower atmosphere. I don't know what that layer is called, but it more affects just the lower part of the atmosphere, but it does affect it. So basically, if enough ash and gases go up into the air, you can get basically 2 effects, and they're the exact opposite. One thing that can happen is that basically you get a big layer of greenhouse gases, and so then the Earth can heat up. You can have a rise in temperature because you now have a bunch of greenhouse gases that have suddenly been expelled into the atmosphere. So that's one thing. The other thing, which is the exact opposite, is that so much ash goes up into the atmosphere that sunlight can't come through it anymore. And so then the Earth's temperatures drop because no more UV light can come through. So, and you don't know, there's no way to know exactly which one is going to happen until it's already happening. So yeah, when there's like mass extinction events throughout Earth's history with volcanoes, it's either, everything got really, really hot or everything got super, super cold. It can go either way. Yeah? What are the benefits of my job? Because it is a dangerous job. The benefit to my job is it's super duper fun. There is a little bit of a slight danger to it, but ultimately I wear protective gear, so my sleeves, these are made out of Kevlar, so that's what's protecting me from the heat, so it doesn't bother me so much. A lot of people can't see it. These are actually safety glasses. They just look like real glasses because I'm blind. But I don't know. Ultimately, benefit is that I get to talk to people and I get to share my knowledge. It is super duper fun, and they do train us a little bit to make sure that we can do this safely, that we don't throw lava at anybody or ourselves first. Yeah?
Do you require a special type of metal to handle it, or is the metal high enough?
Yeah, do we have a special type of metal? So it's not, I guess, really special, but it is a specific kind. It's steel. So this one specifically is black steel. That's what the engineer told me. This one is stainless steel. Both of these steels are not going to melt until about 1,500 Celsius, though. Lava only comes out at 1,100. So we're far enough off that melting point that it's not going to do anything. Yeah?
So when I step outside, I smell
Uh-huh. Yeah, when you step outside, it smells a lot of sulfur. Is that from the active volcano? So that's actually not from the active volcano. That's actually just from our hot water. So our hot water, especially in the city, it is geothermal water. So groundwater that's been heated up by the ground just because it's so super duper hot under there. And it just is because there is a lot of sulfur in volcanic rock. And so when we bring up this hot water that's been sitting in that volcanic rock, it has this very sort of sulfury, eggy smell. But it's not toxic sulfur. This is not that, really terrible hydrogen sulfide, sulfur dioxide. It's just a little bit of sulfur mixed into that water, and it's just enough to give that sort of really eggy smell. I know, when I first moved here, everybody always said, oh, you'll stop noticing it after a while. That never happened. I do notice it. It just doesn't bother me anymore. I guess that's really what happened.
I can't smell it.
Yeah?
That water from the lagoons, is that beneficial? You should sit in?
Yeah, like the Blue Lagoon water?
Yes.
Yeah, the Blue Lagoon water. Is it beneficial to sit in? Yeah, it is. It provides a lot of, it's like skincare. It's like basically like a skincare bath. Silica has natural healing properties. It provides a lot of nutrients for your skin. It does dry it out, so that you just have to, moisturize it again. But the blue water is known to heal a lot of skin conditions, eczema, psoriasis. So people in Iceland, if you've been diagnosed with psoriasis, you actually get a medical card to go to the Blue Lagoon because the water has healing properties about it. So yeah, it does. Huh. Yes? Does lava actually, is it existent?
When did it actually exist? Yeah, when did it actually exist?
When did it actually exist? So lava exists, thank you, sorry. Lava exists all the time. We have lots of lava all over the place. It's underneath our feet, granted very, very deep beneath our feet, all the time. And then just sometimes it comes up and it can erupt. We actually have an active eruption in Iceland going on right now, and it's erupting out fresh, brand new, newborn lava right now, and it's just about 45 minutes away. So there's always lava around. Mm-hmm. And so I'm just going to quickly tell you about that, the current eruptions, because I do have to start wrapping this up. But with the current eruptions, yeah, we've had 5 in the last few months. By the way, they are the effusive kinds of eruptions. These are the gentle kinds, basically as gentle as a volcano can be. These eruptions, we are not really that concerned at all about human life, I guess, with it. We're not worried about them hurting people, really, because they're very slow moving and they're gentle. So it's just sort of lava flowing around on the ground. The problem with them is damage to infrastructure because it happens to be near populated areas, the town of Grindavik as well as the Blue Lagoon. So what's been done is safety barriers have been built around those structures that they want to save. But with every eruption that comes, more lava keeps getting added into that. And so this was a concern a couple of eruptions ago, and that concern is starting to come true. The walls are not tall enough anymore. With 5 eruptions, it's a lot of lava. And so a few days ago, lava did go up and over one of the berms, one of the safety barriers. Again, it's not near, it is sort of near the Blue Lagoon, but it's far enough away, it's not like a concern of it's gonna burn down the Blue Lagoon. But it did start going over it, so what they're now doing is that they have crews out there, they're spraying that lava coming over the wall with a fire hose. They have firemen out there and they're spraying it, and this is an absolute real technique. This is not the first time Iceland has done it. I actually think it's the 3rd time that they've had to do this for different eruptions just throughout history. And it does work. They're not trying to stop the volcano. You can't stop a volcano. What they're trying to do is mitigate damage. They're trying to slow it down because what they've done in slowing that lava coming over the wall, they've now built a new wall so that they can create more of a stoppage and keep it contained. So that's what they're doing right now. It's definitely a funny looking technique because there's guys with a hose standing there spraying lava, but it really does work. And there is new equipment coming into Iceland. They're bigger, larger scale equipment, so hopefully it's going to help us here in the future once it comes into the country. But yeah, that is sort of what's going on, and we'll just have to see where it goes from there. All right, this one's going to be my last one. Has anybody ever died from spraying the lava? No, nobody has ever died from spraying the lava. All the people out there that are, protecting us from that and spraying it, they're wearing special gas masks and they're wearing special gear so that they don't get burned and that they can breathe just fine, so they don't have to inhale the gases. So yeah, nobody out on the cruise has perished due to the volcanoes. But all right, that one was going to be my last one. I got to give you my last fun fact. So my last fun fact about lava, humans can't sink in lava. It's impossible to sink in it because lava is 3 times denser than water. Humans are mostly made of water. So it's because of the density difference between us and the lava that makes it physically impossible for us to sink in it. That's really good news.
We just get stuck.
Yeah, but if any of you do one day trip and fall into the crater of a volcano, you don't have to be worried about drowning in it. You're not going to drown in the lava. Yeah, all you're going to do is you're going to splat onto it, you're probably going to stick, you might scream a little bit, and then you'll just turn to ash dust and blow away in the wind. So that's what you got to worry about. It's totally fine. All right, so with this, I got to thank you so much for coming to the show. I hope you enjoyed it. Thank you.
Subscribe if you liked it.
If you did enjoy it,